Okay then guys, let me just run you through a couple of brief concepts in regard to the Argand diagram, all the concepts and ideas that are associated with it. One thing I didn't probably mention in previous sections is that if we want the real part of a complex number z, say, then we can denote that by capital R lowercase e re of z, or similarly im z is the imaginary part, re of z is the real part of the complex number z. So here's a xy axis, and we can represent called an Argand diagram in the context of complex numbers, and we can represent complex numbers by means of their Cartesian coordinates. So if you take the x-axis to be the real axis then, and let's take the y-axis to be the imaginary, the number 2 plus 3i can be represented by the coordinate 2, 3. So let's just put that in the diagram. There's the coordinate 2 and 3. Go along 2 on the x, up 3 on the y, as is customary. And we can also draw a line, of course, to represent it in terms of a vector. So we can think of complex numbers as vectors as well, and manipulate them by moving vectors around as we're accustomed to, and adding them, subtracting them, and similar things as that. So we can think of them as Cartesian coordinates, or as vectors, or whichever one is convenient in the context of a particular problem. And similarly, we can think about them in terms of polar coordinates as well, because sometimes it's convenient to interpret the problem in terms of polar coordinates, r, theta. This length r, when you've got a complex number like this, what you can do is you can do simple Pythag. This length, of course, is 2. This length is 3. Square both sides and add them. 4 plus 9 is 13, and square root, and you get the length of the longest side. This is termed the modulus, or the absolute value. The length, these are all concepts associated with the modulus function, and it just simply means the length, and there it is there for that particular example. So the modulus of 2 plus 3i is equal to the square root of 13. Then associated polar coordinates have an argument as well, theta, and as is the case in polar coordinates, we also have a principal argument range here, going from minus pi through to pi. So that's the principal argument. We denote the principal argument by arg of z, and then we denote a general argument, whatever value of theta, by arg. That's the general argument of the function, and the other lowercase a was the principal argument. So that can be any value. So if this was, say, 45 degrees, pi over 4, then you could add any multiple of 2 pi, or take any multiple of 2 pi and write down this is equal to this value, because it has a multiplicity of values here for the capital A argument, the general argument, whereas argz has only one principal value. Okay then, so I think that's about everything I need to say at the moment. It's just a gentle introduction, so all the best in this subsection then, guys, and I'll say a bit more about these concepts in the next little intro in the next part of this section. Cheers!